Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to our MOOCs course on the topic of fundamentals of nuclear power generation. In our last lecture, we discussed about the topic of nuclear fission, which is a part of our third module, and today we are targeting to finish this particular module. That is, in this second lecture, we are looking to finish our third module on nuclear fission. As a brief recap of whatever we have done in the last lecture, you are introduced to the topic of nuclear fission. We now know that whenever a particular nucleus, a fissile nucleus, that is, when it absorbs a neutron, generally a thermal neutron, it is excited to a very high energy level, and accordingly it can go through two different kinds of phenomenon. One possibility is that it can release that energy in the form of gamma photon and come back to the ground state in the form of another isotope of the parent nucleus itself. But the more probable option for the fissile nucleus is for this to undergo the fission process, that is to get splitted into two lighter nucleus or lighter some other kind of isotopes. So, according to the nature of these materials, you are introduced to these definitions of fissionable, fissile and fertile materials, where the term fissionable is associated with any particular nucleus which can be fissioned with respect by striking it either by thermal neutron or fast neutron, but fissile, the term is used exclusively for the nucleus which can undergo fission only after absorbing a thermal neutron and also can sustain a chain reaction following that fission, whereas fertile are those which can't be fissioned through a thermal neutron, but can be converted to a fissile isotope. Like the examples as we have seen, uranium that is 92U235 is the only naturally occurring fissile isotope, but there can be a couple more which are generally artificially produced, but are very commonly used. One is uranium 233 and other is the wear grade isotope, which is plutonium, that is 94Pu239. Whereas an example of fertile material, there are several, but very common example is generally thorium 232. Thorium is actually having an atomic number of 90, and other is uranium 238, that is 92U238, where this uranium 238 can be converted to plutonium 239 and thorium 232 can be converted to uranium 233. Just one odd coincidence you can look at. If you go through this example, say first for uranium 233, it is having 92 number of protons, and how many neutrons it has? It has 141 neutrons in its isotope. Now come to uranium 235, again it is having 92 protons and 143 number of neutrons, and in case of plutonium 239, it is having 94 protons and if I calculate, it is 145, I think, number of neutrons it has. Whereas, now if you take a look for these two fertile isotopes, for thorium 232 it is having 90 number of protons and 142 number of neutrons, and for uranium 238 it is having 92 number of protons and 146 number of neutrons. Can you see this coincidence? It is quite odd. I do not have any explanation for this, but generally for the fissile isotopes you will see there is a odd even or even odd kind of combination in the nucleus, that is even number of protons and odd number of neutrons, whereas for the fertile isotopes you have an even combination, that is both even number of protons and even number of neutrons. Again I repeat, I do not have an explanation for this. If anything at all exists, nuclear physicists may give some idea, or it may be just a coincidence, but this is a quite interesting thing to observe. Now, if we move further, once you are introduced to this topic of fissile and fertile isotopes, then the next thing that we discussed is the fission fragments. Fission fragments refer to the two daughter isotopes which are produced because of the fission of some kind of fissile isotopes. Fission fragments are generally radioactive in nature, and therefore, they go through several steps of decay. But another interesting fact is that fission fragments generally vary in their mass numbers, or it is highly unlikely that both the fission fragments will be having the same mass number. Rather, they vary in the magnitude of their mass numbers, and the difference between their mass number keeps on reducing with increase in the mass number of the parent isotope. That is, the difference between the mass number of two fission fragments produced by uranium-233 fission will be higher than the same for plutonium-239. Then we discussed about the effect of energy of the neutron on the fission, on the cross sections. Actually, I should have written here the dependence of En on sigma f and not what is written here. We now know that we can get generally three kinds of regions, where the most interesting one is the initial 1 by V region, which refers to this particular part, where the both fission and non-fission capture cross section almost linearly reduces with the energy of the neutron, and the most interesting of that is generally the thermal neutron part, because there the fission cross section is found to be quite high. And we finished the last class discussing or introducing the term moderator. Moderator refers to the material which is used in the nuclear reactor to reduce the kinetic energy of the neutrons, so that it can be converted from initial fast neutron levels to the thermal neutron levels, and thereby increasing the possibility of fission, because we always have to remember that at lower energy level the fission cross section is much higher. Possible reason can be lower energy level means lower velocity of the neutron, and therefore, the neutron has much longer time to spend in close proximity of the nucleus, and therefore, much bigger chance of having any kind of interaction. So, today we shall be focusing primarily on this topic of moderator, and we shall be seeing how we can reduce the energy, or at least we shall be doing lots of mathematics here to see how can we calculate what is the energy the neutron shall be having, or neutron will be having after undergoing collision with any kind of moderator nucleus. So, I am starting with a slide with which I finished the last lecture. I have to do lots of mathematics here, but it is quite odd to present that on slides, but I do not have the option of using board, and that is why I am trying to keep it as much interactive or as much step by step as I can. Please try to follow the discussions. Here we have one neutron shown by that red dot of mass m, which is moving with a velocity v, and it is approaching a nucleus which is initially stationary. Capital V is the velocity of this nucleus, which is equal to 0, and its mass is m. And once this neutron collides with this nucleus, then it transfers a part of its momentum and kinetic energy to the nucleus, and accordingly both of them gets deflected to certain angles. Like here, theta refers to the angle with which the neutron gets deflected from its original path of motion. V prime, small v prime is the velocity of the neutron after collision, whereas capital V prime is the velocity of the nucleus. Now, if we write the conservation of energy, then as this being elastic scattering or elastic collision, both kinetic energy and momentum will be conserved. So, as per the conservation of energy, initial before collision the energy is half m v square, this part where 1 refers to the state before collision, 2 refers to the state after collision. So, after collision total energy is the summation of the kinetic energy of the neutron, which is this, and the kinetic energy of the nucleus. Both being equal, let us use this term E L to denote the total energy available in the system before and after collision. And as per the conservation of momentum, initial momentum is m v, or the momentum of the neutron alone, and after collision the momentum is the summation of momentum for neutron and momentum of the nucleus. Both should be conserved. While we can continue with this particular approach, but this is generally termed the lab scale approach. Here this subscript L refers to the lab scale, but generally it is quite convenient to do the rest of this mathematical procedure following something called the center of mass approach. Center of mass is an hypothetical object which is having the total mass of the system. Like here this Cm refers to the center of mass. This hypothetical object is having the total mass of the system, that is its mass will be small m plus capital M, that is mass of neutron plus mass of nucleus, and also it is moving with such a velocity that its momentum is equal to the total momentum of the system. Then for the center of mass we can write its total momentum will be small m plus capital M, which is its mass, into some velocity which is moving. This should be equal to the momentum of the system, which is the momentum of the neutron alone before collision. The center of accordingly we can calculate the velocity of the center of mass. Now, the center of mass approach has certain advantage. If we choose this one as the frame of reference, accordingly we can calculate the relative velocities for both neutron and nucleus, and as we shall be seeing shortly, it will provide you three different advantages. Firstly, total momentum of the CM system, or as per the center of mass system, total momentum will be equal to 0. The magnitude of the center of mass velocities, that is magnitude of the velocities of neutron and nucleus as per this new approach, that will not change after collision, only change will be in their directions. And thirdly, total energy of the CM system will be less than the lab system, because the center of mass itself is moving. Yes. We shall be proving all of them. Now, this is the modified situation before and after collision as per the center of mass system. Here small u refers to the relative velocity of the neutron as with respect to the center of mass, and this capital U or minus capital U refers to the relative velocity of the center of relative velocity of the nucleus with respect to again the center of mass. Minus sign indicates that it is in the, here we have taken the direction for motion of neutron to be positive, accordingly capital U is negative. And after collision they get some velocity as small u prime and capital U prime, and theta c refers to the angle as per the center of mass system. So, now small u can be, and this being relative velocity of the neutron with respect to the Cm. So, it will be of course velocity v minus v of Cm, and putting the expression for v of Cm we get this. Similarly, capital U will be equal to v capital V minus v Cm, capital V is 0. Remember the nucleus we have assumed to be stationary. So, capital V this is equal to 0, and accordingly we get an expression for capital U as well. So, now we know the relative velocities or the velocities for both neutron and nucleus as per the center of mass system. So, the total momentum we can calculate according to the CM system should be equal to small m into small u plus capital M into capital U, and if you put the expression it is equal to 0, which is the first point I have mentioned. As per the center of mass system, total momentum will be equal to 0 both before collision and after collision. Now, total kinetic energy as per the CM system should be equal to the same for neutron plus the same for the nucleus. Here of course, we are using small u and capital U because we are doing everything with respect to the CM system, and accordingly we can get a simplified expression, and we can relate that to the original velocity of this neutron, which is the velocity as per the lab scale. And here we rearrange the term so that we get finally mu by small m into EL. Remember, EL was the kinetic energy as per the lab system, which was half m v square, small v square. Here mu can be seen as a reduced mass, which allows us to compare the kinetic energy across both frames of reference, and it is given as small m into capital M by small m plus capital M. Now, one important you can say this approximation, but this is quite it is not a bad one actually. We know that mass of a neutron is slightly above 1 AMU, whereas the mass of the nucleus is it will be quite close to the atomic mass of this one expressed in terms of AMU. So, it is very much likely that if we get this quantity, this is most likely to be equal to the atomic, this is most likely to be equal to the mass number of that particular nucleus. Accordingly, we do the substitutions to get mu equal to A by 1 plus A. So, putting this back into the original expression, we get the energy as per the center of mass system divided by the energy of the with respect to the lab scale system is approximately equal to A by 1 plus A. Now, whatever may be the value of a, surely this ECM will be less than EL, that is this ratio always has to be less than 1, because the denominator is always higher than numerator. So, that proves the third point that I have mentioned earlier, the energy with respect to the CM system should be equal to, or should be less than rather, with respect to the compared to the energy with respect to the lab scale system. And the difference being the center of mass itself is moving, and so itself is having some kinetic energy. Let us move forward now. The same diagrams are reproduced here, and we are writing the conservation of momentum with respect to the CM system. So, small u prime and capital U prime refers to the velocities of neutron and nucleus respectively with respect to the CM system. So, we write the conservation of momentum in this form. Now, this being a vector equation, we can always separate that into as per the components, and sticking to our 2-dimensional representation. This is according to, let us say this is our x direction and this is our y direction. So, accordingly, before collision the momentum of the system is equal to m into u contributed by the neutron, and this one is contributed by the nucleus, the direction being opposite, we are having this minus sign in between. And after collision, this u prime is having the cos theta c component in this direction, and again this is also having the cos theta c component in this direction. So, we get this particular expression, and similarly we can also represent, or we can also get the y component of the same equation. Before collision, both the components, that is neutron and nucleus, are moving in the x direction. So, the y component is 0, but after collision we can have an y component. So, from the second part we get u prime is nearly equal to a into capital U prime, and putting that back into the first expression we get small u is nearly equal to a into capital U. Now, conservation of kinetic energy as per the CM system. Conservation of kinetic energy or energy as per the CM system can be calculated as this is the kinetic energy before collision, this is the kinetic energy after collision. Small u and capital U are the velocities with respect to the CM system before collision, small u prime and capital U prime are the velocities after collision with respect to the CM system. So, as kinetic energy has to be conserved similar to momentum, we can equate them, and by using these substitutions we finally attain this, which proves capital U and small u prime are equal, and same applies to small u and small u prime. That means, we can clearly see that the magnitude of velocities for both neutron and nucleus remains the same before collision and after collision. However, before collision both of them are moving only along the x direction, but after collision there is a change in their directions while magnitude remains the same. So, these are the 3 points that we have, or 3 certain characteristics for the CM system that we have mentioned earlier, which are proved here. Now, let us move to what we are trying to find. We know that the objective of having this elastic scattering is to reduce the kinetic energy of the neutron. So, let us calculate the ratio of this energy before collision and after collision. After collision, before collision the energy was this half m v square, after collision if v prime represents the actual velocity, then velocity with respect to the lap scale, that is, then this is the kinetic energy of this, and correspondingly we get this to be equal to the velocity squared ratios. Here on the left I have the diagram, this is as per the lap scale system and this is as per the CM system. Theta is the angle at which the neutron gets scattered as per the lap scale, whereas theta c is the angle at which it gets scattered as per the CM scale. Now, we can velocity being a vector, we can get as per their components, that is v prime cos theta has to be equal to v CM plus u prime cos theta c. Basically, here just seeing this, this is the v prime, this is the actual velocity, and if we take their components, this should be, this is the u prime, and then let me rewrite, say relative velocity, this is u prime and this is the v CM and this is u prime. or I should say, okay. Then if we follow the triangular law of this vector addition, then we can add them together, and this resultant should be the actual velocity v prime, where theta represents the intruded angle, this angle is the theta, and accordingly we can write this particular expression, that is v prime cos theta c should be equal to the VCM plus u prime cos theta c. V prime cos theta is equal to VCM plus u prime cos theta c, and their sine counterpart, taking the ratio, the angles as per the lap scale, which is theta, and angle as per the CM scale is theta c, we can get a relation between them. And then we substitute couple of relations which we have derived earlier. You remember, if you go back couple of slides, the VCM was expressed earlier in terms of V, and u prime was also expressed in terms of V. So, we put this back and we arrive at this particular expression, or assuming capital M by small m to be equal to A, we get this tan theta to be equal to A sin theta c divided by 1 plus A cos theta c. So, using this vector combination or the vector components, we can find a relation between the angle of scattering as per the lap scale, which is theta, and as per the CM scale, which is theta c. Now, we squared both the equations and add them together, then this is where we get, and by changing the sides or dividing this entire equation by v square, we arrive at this particular form, and putting capital M by small m nearly equal to A, this is what we end up to. This is of what our interest, what we were looking for. Often we define a collision operator as alpha equal to A minus 1 by A plus 1 whole square. Then 1 minus alpha is equal to 4 A by A plus 1 whole square, and 1 plus alpha is equal to 2 into A plus 1 plus A square by A plus 1 whole square. If we put this back to the equation that we have derived here, this one, we relate to this 1 minus alpha and 1 plus alpha. This is a final expression, that is E prime equal to half into 1 plus alpha plus 1 minus alpha cos theta c into E. It is an extremely important relation. You remember, this E is the energy of the neutron before collision, and E prime is the energy of the neutron after collision. Cos theta c is the angle of deflection or angle of scattering as per the CM system, and alpha is, this is the definition. So, alpha is a function of only the mass number of the moderator nucleus. So, it is a property of the moderator. For different moderator, value of A will be different, but once a moderator is given, alpha is a constant, E is the kinetic energy before collision. So, suppose I give you a pair of neutron and nucleus, then both E and alpha are specified, then the energy after collision is governed solely by the angle at which it can get deflected. There can be several situations, say when theta c is equal to 0, that is no scattering of neutron, or neutron is not at all changing any direction. That basically signifies there is no collision, the neutron has not at all collided with the nucleus. And if we put this expression, then you will get E prime equal to E. There is no loss of energy because there has not been any collision. If we put theta equal to 90 degree, then cos theta equal to 0, E prime is equal to half into 1 plus alpha into E. More interestingly, if we put theta equal to 180 degree, that is, the neutron is having a complete change in its direction and is going back from wherever it has come from, which is often referred as a head on collision. For 180, theta c equal to 180 degree, cos theta c equal to minus 1, and accordingly we get E prime is equal to alpha E. It is the maximum energy loss that a neutron may suffer. Like, we can also calculate this, say this expression for E prime is given to us now, and as I have mentioned, for a given neutron nucleus pair, capital E and alpha both are constant, and therefore, value of E prime depends solely on theta c. So, we can always calculate what is the value of theta c for which the E prime becomes a minima, and if we do the calculation as d prime d theta c, this is differentiate this with respect to theta c and equate that to 0, then this should give you theta c is equal to pi or 180 degrees. and you can also check that this actually refers to a minimum value for this E prime. That is, when there is a head on collision between neutron and the stationary nucleus, then the neutron is expected to suffer maximum amount of energy loss or maximum amount of loss in its kinetic energy, and its magnitude is alpha into E. That is, it is again depending on alpha. Now, alpha in turn depends on A as per this relation. So, for different value of A, we can get different values of alpha. Say for example, what is the lightest possible or smallest possible value for A we can have, or the lightest possible element? Of course, that is A equal to 1, that is, that refers to hydrogen. If we put A equal to 1 here, then alpha equal to 0. So, if we use, that is 1 each 1, that is proton as a moderator, then alpha equal to 0, and E prime is actually half into 1 plus cos theta c to E, which is the maximum possible or smallest possible value of kinetic energy after collision that we can have using any moderator. And again, this depends on the value of theta c, the actual value of E prime. So, if we now use the head on collision, that is theta equal to 180 degree, then E prime equal to 0. That means, it refers to a complete loss of energy. Or you can say, if a neutron of whatever may be the initial energy level of the neutron, it comes and collides with a proton, collides with a hydrogen nucleus and suffers a head on collision, or you can say a neutron of any energy coming and having a head on collision with a hydrogen nucleus. Head on collision means it is having a 180 degree change in its direction, then it is expected to lose entire of its energy, or its kinetic energy after the collision will become 0. So, then what is the gist that we can get from this entire discussion? Of course, theta c is something not in our control. E is the energy that we have from the incoming beam of neutron, and our target is to reduce this E to the thermal neutron level at the earliest. Of course, in a moderator, generally the neutron requires to go through repeated collisions before it can reach to the thermal neutron level. But if you are talking about a single energy reduction in a single collision, then E is the energy with which it is coming, and we have to choose a proper moderator material. Theta c is something that is not in our control, rather it is more a probabilistic definition. A neutron can get deflected to any possible angle after having a collision with this. Then what we can control, that is of course this alpha, or rather we can control this A. Then what conclusion can we draw in terms of the preferable value of A so that we can have a larger reduction in the energy? We should ideal cases having A equal to 1, because for any given value of theta, that gives you the lowest possible value of E prime, and hence we should always want A to be as low as possible. A smaller value of A will give you a much larger reduction in energy. Just compare this particular case situation with something that is having a very high value of A. Like say, if we take uranium 238, that is A equal to 238, then alpha is equal to 237 by 239 whole square, which is virtually equal to 1, and if you put the value of alpha here in this original expression, then correspondingly E prime is equal to alpha equal to 1 for that is the maximum limit of alpha that we can have, it is approximately equal to 1 or tends to 1, and if you put alpha equal to 1 in this expression, then this term goes to 0 and we get E prime nearly equal to E. That is, there is hardly any reduction in the energy of the neutron. So, while when theta equal to 0, that is no collision situation, we can't have any reduction in energy. Also, if the moderator nucleus is having very high mass number, then also the energy reduction is extremely small or almost insignificant. So, it is always preferable to use a smaller value of A. But practically the change or the in the direction or the value of theta is not something that is in our hand. Rather, it is possible to have any value of deflection or any scattering angle. Therefore, we need to go to some kind of statistical averaging or some probability distribution. A probability distribution function can be defined as number of favorable events scattering between some angle theta c and d theta c divided by the total number of events. Let us discuss this with respect to this diagram. Here a neutron is coming whose mass number or its mass is assumed to be nearly equal to 1, and it is striking a nucleus which is situated here. Initially nucleus is here, that is at the center of this circle. After the collision, the neutron can get scattered into any possible direction. Then this probability distribution function says what is the probability of finding a neutron in a very small angle around this theta c, or probability at angle this theta c. If we take very small infinitesimal angle this d theta c, it is an infinitesimal small solid angle you can say, then this function should be equal to the amount of area available over this infinitesimal portion through which neutron can pass through divided by the total area of the sphere. That is, the neutron can pass through any possible direction of a sphere or as per the any of the rays of this sphere. So, if capital R represents the radius of this sphere, then total area available is 4 pi r square, and the area of this infinitesimal small portion, then how much is this? Here we are talking about this particular segment basically. Here 2 pi r sin theta is the corresponding thing multiplied by d theta c, that represents the thickness of this particular conical portion, and so this ratio represents your probability distribution function. Assuming isotropic scattering, because isotropic scattering refers to in all possible direction the intensity of scattering remains the same, and also taking r equal to 1, this reduces to sin theta d theta c by 2, or you can also write this as minus half of d of cos theta c. Now, we have already seen E prime is equal to half into 1 plus alpha plus 1 minus alpha cos theta c into E. So, cos theta c can be represented in this form, and d of cos theta c can be represented like this. So, take it back here, then what we are getting is P prime d E prime is equal to, or this probability distribution function can be represented as minus d E prime divided by 1 minus alpha into E. Finally, a very important concept that is quite often used to characterize this moderator. Firstly, just waiting here in this slide. So far, we have discussed if one neutron collides with the nucleus, then how much decrement in energy it can have. That we have seen that depend on the kinetic energy, that is dependent on the kinetic energy of the neutron, very much dependent on the mass number of the nucleus, moderator nucleus, and also depending on the angle of scattering. But whenever a beam of neutrons strikes a nucleus, we now know from our previous modules that it is not a job of a single neutron, rather we need to supply a large number of neutrons to have any significant rate of interaction, because most part inside the nucleus is hollow or void. Now, whenever such a beam of neutrons is approaching a nucleus, it is expected to have all possible scattering angles. That is, while some neutron may get scattered by say an angle of 10 degrees, some other may get scattered by 120 degrees, and maybe just 1 in a million is suffering some kind of head on collision. So, this probability distribution function that allows us to get an idea about the probabilistic energy distribution over a sphere around the nucleus, initial position of the nucleus, that is. And accordingly, we can calculate the average energy of the neutron after the collision as this thing. We know E is the initial energy. So, if the after collision the maximum possible value of energy it can have is E, and similarly the lowest possible value it can have is equal to alpha into E, which happens when theta equal to 180 degrees. So, we can perform this integration now. P prime d prime already seen in the previous slide, here we have seen that P prime d prime is equal to minus d prime by 1 minus alpha into E. So, we are putting it back here. Now, E is the initial energy of the neutron and alpha is a property of the moderator. So, for a given neutron nucleus pair, we have this term to be constant, or this denominator is a constant. So, we can perform this integration only over E prime, and we are getting that average energy after collision, average energy of the neutron after collision is just 1 plus alpha into E by 2. But the more important definition is of a logarithmic energy decrement, which is basically the ratio of energy before collision divided by kinetic energy, average kinetic energy, that is after collision. Here we are not at all dealing with a single neutron, rather we are dealing more with a beam of neutrons. As different neutrons in a single beam can undergo different amount of scattering. So, the energy of the neutron after collision also will be varying a lot, but this E prime bar, that is this quantity, averages that over all possible directions. And now, logarithmic energy decrement is represented as energy before collision divided by this average kinetic energy after collision, and take a log of that. So, that we have log E minus log E prime bar. If we put the expression for E prime bar, then this is what we end up to, and putting the expression of this P prime d prime, this is what we are getting, that is integration limits remains the same, because E is the largest possible energy after collision and alpha is E is the smallest possible energy after collision for any given value of alpha. Now, how to perform this integration? This looks a bit complicated, because we are having a log of E by E prime that is available, and E prime is the independent variable also. Let us assume some chi is equal to E prime by E. So, putting that here, d chi will be equal to d prime, because capital E is a constant. Capital E, we know this prime will be equal to d prime by E. So, that can be put back here, and actually I think I have made a typing error here. I have made a typing error here. This E should not be a part of this expression. It is because d prime by E is equal to this particular term. So, 1 minus alpha being a constant comes out of the integration, and another important change is the limit of the integration. Now, when E prime is equal to E, I am struggling to write this particular symbol, chi is equal to 1. So, lower limit becomes 1, and the upper limit for E prime is equal to alpha into E. Accordingly, this is equal to alpha. So, this is the upper limit. Now, putting these expressions, and also as I mentioned, this E goes off here, this E is not present, this, then we have log x dx. We can integrate this to over the given limits of 1 to alpha to get 1 plus alpha by 1 minus alpha of log alpha. So, logarithmic energy decrement, you can see the final expression that we are getting, that includes only alpha, or it is a sole function of the moderator. It does not depend upon the energy of the neutron or initial energy of the neutron at all. So, average decrease in the energy level of a neutron beam, that very interestingly is not at all dependent upon the energy of the neutron with which it is coming, rather it depends only on the moderator, or it is a sole function of the moderator nucleus. Now, we know alpha is equal to a minus 1 by a plus 1 whole square. So, if we put this back, we get zeta is equal to this excellent expression, which is again a sole function of capital A, and for any value of capital we can calculate the value of corresponding energy decrement or average decrease in the energy. Like when A tends to 1, zeta tends to 1, and E prime bar is equal to E by small e, which is the maximum possible decrease in the average neutron energy. When there are number of generally we need to have several collisions for the neutron, so that its energy can be reduced from some given initial level to some given final level. This logarithmic energy decrement also allows us to calculate the total number of collisions required to slow down the neutron from an initial level to a final level, and this can be calculated using the definition of zeta. It can be calculated as log of E n initial by E n final divided by zeta. These are some sample values. Let us say when H is equal to 1, that is hydrogen A equal to 1, if we put that, then directly we are getting zeta equal to 1, and corresponding collision to reduce, say if E n I is equal to 2 MeV and final energy is equal to 1 electron volt, then we are getting the corresponding 15 collisions will be required. These all numbers are actually scaled up, that is if we are getting 14 point something, that has been converted to 15. So, getting 15 collisions for this. Similarly, when d equal to 2, you can calculate the value of zeta. Okay, from the source I have taken, this does not seem to be correct. If you put the numbers, it should be 725, but it will require 20 collisions to reduce a neutron energy from 2 MeV to 1 electron volt. Similarly, you can see, like if we take a very heavy isotope like around 238, value of zeta is extremely small, 0.008, and more than 1800 collisions are required to have this amount of reduction. Just compare this number. For hydrogen it is only 15, whereas here it is 1812. So, very large number of collisions will be required, and we can clearly see as the number of collisions or as the mass number of the moderator nucleus goes on, like in this direction, the corresponding number of collision is also increasing continuously as the value of zeta is decreasing. Quite often the moderator material comprises of several kinds of isotopes or several kinds of elements. In that case, we need to define an average value of zeta or weighted average, and that is defined as the summation of scattering cross section, summation of the scattering cross section into the logarithmic energy decrement for any component divided by the summation of the scattering cross section for all components. This is slightly confusing here, this symbol here refers to summation, however, for macroscopic cross section also we are using the same symbol. However, here it refers to the summation only. Then what should be the desirable properties a moderator should have? This is something we have mentioned earlier. A moderator must have large scattering cross section and low absorption cross section. If the scattering cross section is high, it will be able to capture a good amount of energy reduction in just a single collision, whereas it should have very low absorption capacity. If the moderator itself starts to absorb the neutrons, then there will be a neutron dart that is created inside the nucleus, and the reaction can sustain, the chain reaction. But now we are also seeing that having high sigma is alone is not sufficient, rather the logarithmic energy decrement also needs to be high, so that in a small number of attempts we can reduce the energy of neutron from some very high value to some reasonably low value, generally at the thermal level. But what else the energy decrement can depend on? That should depend on the number of nucleus, moderator nucleus that is present in the system. If the number of moderator nucleus is more, then there will be more number of interactions, or the chances of interactions scattering, that has to be directly proportional to the number of moderating nuclei that is present in the system. So, we want a high nuclei density for the moderator. Now, these three terms quite often are combined into these two definitions, moderating power and moderating ratio. Moderating power is defined as zeta n into sigma s, that is it is the product of these three quantities, logarithmic energy decrement into the nuclei density of the moderator into the scattering cross section. Here this capital sigma s refers to the macroscopic scattering cross section, because we know this scattering cross section or any macroscopic cross section is sigma n into the nuclei density into the microscopic cross section, and we can use say S subscript for both macroscopic and microscopic cross sections. This in the previous slide, of course, the same symbol was used to denote summation, but here it is the macroscopic cross section. This moderating power shows the efficiency of moderator in slowing down the neutrons. It is quite often called the macroscopic slowing down power, or MSDP. Other is moderating ratio, which is the energy decrement, logarithmic energy decrement multiplied by the ratio of scattering to absorption cross section, which we can write as if we multiply with both numerator and denominator with n, then we can convert that to the macroscopic cross sections. So, it shows the efficiency of the moderation without absorption. If so, what kind of values for this moderating power and moderating ratio we should prefer? Of course, both should be high. We should prefer a higher value of moderating power, because in a single collision larger amount of energy reduction is possible. Similarly, moderating ratio also should be high, because for given amount of absorption or given amount of scattering, the absorption should be very low. This is some numbers of some of the isotopes that are present earlier. Like we have seen we have seen that hydrogen and deuterium both are excellent as moderator. Hydrogen having a mass number of 1 is the best possible material that we can have as moderator. But the problem for hydrogen or deuterium is that they are gaseous in nature, and therefore, the nuclear density or number of nucleus present per unit volume should be very low. That is why those materials are generally not used, rather they are converted to their compounds in the form of common water or the heavy water, and those are used as a moderator. These two are the most preferred moderator that we can have in any kind of nucleus, whereas the common nucleus or common water is the most preferred choice. Heavy water is generally used in CANDU types of reactors or reactors where the neutron is highly enriched. We shall be discussing on neutron enrichment in the next module. And you can see, to reduce the energy level from say 1 mega electron volt to the thermal neutron level, whereas the common water requires 19 number of collisions, heavy water requires 35. There are a few other materials also quite often used, like helium and beryllium has been tried in a few reactors recently. Boron not the best choice, because its moderating ratio is very low. Boron has a high absorption cross section. So, while its slowing down power is not that bad, you can see the helium has an extremely low slowing down power, something like this, whereas the it is the lowest among this, and this is the highest. So, as per the macroscopic slowing down power or moderating ratio, definitely common water is the best choice, whereas the helium is extremely poor from that point of view. Whereas, if you compare from moderating ratio point of view, this is not quite bad, but this is extremely high, because deuterium has an extremely small absorption cross section. It hardly absorbs any neutron, that rather whatever neutron comes, that gets scattered, and therefore, it is an extremely high moderating ratio. On the contrary, as I just mentioned, boron has extremely small absorption cross section, because it absorbs a good amount of neutrons. Therefore, it is not at all a good choice as a moderator. Carbon, that is graphite, that is also used in certain kinds of reactors. It also has a quite high moderating ratio, because it does not absorb too much, but its moderating power is lower, even lower than boron. So, if we see only from moderating power point of view, this looks to be the best one. However, moderating ratio point of view, this is extremely good, the deuterium or heavy water. But these 3 parameters alone are not sufficient to justify the choice of a moderator. Rather, there are several associated issues that also we must look into, like the chemical stability. As in nuclear reactor, we expect to have high temperature involvement. Quite often, the certain materials may become soft at higher temperature, or may start to go through some kind of chemical reactions. So, it should be chemically compatible with other materials present inside, and also should be strong enough to sustain higher temperature. That structural compatibility is the issue. It should not get deformed, or should not just buckle down at higher temperatures. That is another reason of not using gaseous material, like carbon or graphite. Well, carbon we can use in the form of gaseous materials like carbon dioxide, etc. Graphite is always a much better choice, and that is generally used not in the reactor where we have water present, rather it is used where gas is used as the coolant. So, more in gas cooled reactors, graphite is used as a moderator. whereas beryllium has been tried in certain reactors. Another, the cost and availability. I have mentioned heavy water is having a very high moderating ratio and its moderating power is also not that bad. So, it is probably the best choice among the 6 that those are listed here, but it is extremely costly. On contrary, this is cheap, very easily available, and handling this one is also not at all difficult, and that is why common water is generally the most preferred moderator that you will find everywhere. So, that brings us to the end of this particular module. Let us try to summarize whatever we have learned in our third module. We have seen that absorption of thermal neutrons by fissile nucleus can lead to fission or non-fission capture depending upon the relative fraction of fission cross section or absorption cross section. Uranium 235 is the only natural occurring fissile isotope which can undergo fission only by absorbing thermal neutrons, but plutonium 239 or uranium 233 can also be easily produced. There are isotopes like uranium 238 or thorium 232 which are fertile isotopes. They can't undergo fission after absorbing thermal neutrons, but can get converted to some kind of fissile nucleus, the process which is called breeding. You have also seen that the two fission fragments which are produced because of fission reactions are not likely to have equal mass number, rather their mass numbers will vary, and the difference between their value of mass number that reduces with increase in the mass number of the parent nucleus. Absorption cross section varies almost linearly, that is decreases almost linearly with the kinetic energy or velocity of the neutron in the 1 by v region, but there is also a resonance capture region in between. While the resonance absorption cross sections are quite low for the fissile materials, but materials like uranium 238 can have extremely high resonance absorption cross section, and therefore, it is a zone that better to be avoided, or at least we should try to make the neutron flow through this zone at the earliest in order to avoid the cross section, avoid the resonance absorption. Energy lost by the neutron during a single elastic collision or single elastic scattering is found to be maximum in case of head on collision, and also when the mass number of the moderating nucleus approaches unity. Therefore, it is always preferable to use some kind of moderating material whose mass number is quite low, preferably quite close to 1. And finally, logarithmic energy decrement was defined to express the average energy reduction of a beam of neutrons during a single collision, and it is found to be, very interestingly, it was found to be independent of the initial energy of the neutron, depending rather on the atom mass number of the moderating nucleus only. And finally, it is desirable to have high moderating power and moderating ratio for the selected moderator, along with several commercial factors like cost, availability and other compatibility things. So, that is the end of our third module. There are several other topics which are related to fission reaction, but I thought about keeping that as a part of our fourth module, where we shall be discussing about the chain reactions and the neutron diffusion equation. Thanks for your attention. You shall be having access to the assignments. So, please solve the assignments, and if you have any doubt, where you face any issue, do not hesitate to mail us back. Thanks you.